Suppose you have a force field, not the invisible wall from science fiction, but a force at each point in space, the physics version. You might have that if you're a mass in a gravitational field. So for each unit of mass, you'll have a certain amount of force in a given direction along the field. Or you might be a charge, an electric field, in which case for each unit of charge, you'll have a certain amount of force in that direction of the electric field. And so in fact, a mass in a gravitational field sees a force. A gravitational force is a function of space. Or a charge in an electric field sees a force as a function of space. Now forces do work as you move around. If you are a charge in an electric field and you experience a force in that direction, then you're going to accelerate in that direction, which means you're going to either increase or decrease your kinetic energy, or possibly turn and change direction. And so a force can change your amount of energy, and that means it's doing work on you, and work can be positive or negative. Now some force fields are what's known as conservative, and that means, supposing I have a potential energy like this, if I start here and I move around, I'm going to see a gravitational force, and it's going to be largely making me go faster as I go down the hill and largely slowing me down as I come up the hill. But if I go around in a loop, then if my net work is zero, what that means is that it doesn't change my energy. And if you have that situation, then you can talk about potential energy. So for example, if I have this in gravity, which is our natural thought because it's actually in gravity, then I can think of this as having higher potential energy than down here. Now if I could go around in a loop and I would get a different energy, in other words, if the work wasn't zero, if I went around a loop, then I couldn't really talk about that. I couldn't say this has more energy than that, because it would depend on how I went from A to B. But if it doesn't matter how I go from A to B, then I can talk about the amount of work that's done by the force is always the same, and that means the amount my energy changes is always the same. And I can say that this point has more energy than that point. And so I've got a potential energy difference. And this is where the idea of potential energy comes from. And just as that applies to gravity, it also applies to electricity. And so we have the idea of the electrical potential. So normally if you have a force field and you have some particle, and that particle is moving in that force field. So this particle, maybe this is an electric field, and so this particle is charged, and it's therefore going to have a force in the direction of the field, which is a vector. It's got a magnitude and it's got a direction. And if that particle is moving across the field like that, then its energy is going to be changed by a rate that depends on the amount of force along the direction of that motion. So that component of the electric force multiplied by the velocity that it's traveling, and that's going to be the rate of change of its energy due to that force. So over a small amount of time, delta t, we can write the rate of energy change as the amount the energy is changed, delta E, divided by that small amount of time. And that rate is going to be the force in the direction of the motion times the velocity, and the velocity is just some distance over that amount of time. And we can see this all makes sense if we cancel the divided by delta t on both sides, and then you can see what we've got on the left hand side is the work done. It's just equal to the force along the direction of the motion times the distance it travels. So if I have an electric field and I have a charged particle that moves at right angles to that field, so if I travel along something like that, at each point I will experience a force, but that charged particle experiences the force, but it's always at right angles where it's moving. So it never gets any force in the direction of its motion, which means it never gets any work done by that field. And what that means is that its kinetic energy never goes up or down. And so while it's traveling at right angles to the electric field, it's always experiencing the same amount of energy, and so it's not getting any energy from the field or giving energy to the field. But just because the nature of the electric field, it turns out that it's a conservative force, which means that the net work around any loop is going to be zero. And the practical upshot of that is if I start down here and I take some strange route to get to this point, or supposing I went a different way, both of these things go from A to B, but it turns out I get exactly the same amount of energy given to the particle when I do that. The reason for that is that the energy going along this path plus the energy going along that path is exactly equal and opposite because they've got to add up to zero. And if you go backwards along a path, you're just reversing the sign of delta S, so you're just reversing the amount of work. And so what that means is that the work done by going forwards on both of these paths is exactly the same. And that work done, that energy that it gains or loses going from A to B, has to come from somewhere, and we talk about it coming from the potential energy of the field. So if I'm a particle here and I have a positive charge, and this is the direction of my electric field, I'm going to get energy as I come all the way to B. I can tell that because if I go and get none and then I follow the line exactly, I've got a force in the direction that I'm going. So I'm going to get energy. So work's going to be done to increase my energy. So this is going to be at higher kinetic energy, and so this must be at higher potential energy. Back at A. A must be a higher potential energy. And so you can look at the potential energy in an electric field. And the one extra complication, and this is exactly the same as it was for gravitational fields, is that the amount of potential energy you get in an electric field is proportional to the amount of charge, because the force is proportional to the amount of charge. So for a given electric field, particles might change by a different amount of electric potential energy, but they all change by the same amount of electric potential energy per unit charge. And so to make things simple, we define something called the electric potential, which is just defined as the electric potential energy divided by the unit charge. This is exactly the same as the gravitational potential. We talk about this point here as having more gravitational potential than this point, but if I take a mass and roll it down the hill, I'm going to get different amounts of energy depending on how much mass. So if I have a dam and I put a ton of water down, I'm going to get more energy than if I put a kilogram of water down. And so what's the same between these 2 points is the gravitational potential. For a certain amount of mass, I'll get a certain amount of energy. And it's exactly the same with electric fields. If you have a high electric potential and a low electrical potential, then if you run a certain amount of charge between them, you'll get a certain amount of energy. Now you'll probably recognize the SI unit for electric potential. It's the SI unit for potential energy divided by the SI unit for charge, and indeed 1 joule per coulomb is exactly equal to 1 volt. So if I have a 12 volt battery, then if I put a coulomb of charge through it, that charge will be given 12 joules of energy.